So welcome to this lectures of our system dynamics and control course. Last class we discussed about the single machine infinite bus system, that too the one axis flux decay model. Considering that, we discussed all our analysis, and already we have derived the state space model. And then from the characteristic equation, we found that the damping term and the synchronizing torque and the damping torque, the coefficients of these torque components, we have seen that they're dependent upon some constants. And out of those, K5 plays very important role. In fact, the model we derived is known as Heffron-Phillips model. That was derived by Heffron-Phillips. So they derived few constants, that those constants plays very important role, K1 to K6. And we saw that K5 in fact plays important role in deciding the coefficients of damping torque and the synchronizing torque. Okay, so let us continue the analysis, and by that way we can see that when the system is heavily loaded and with a high gain exciter, always there is a negative damping effect, and hence your system stability will not be maintained. So in order to maintain the system stability, we need another supplementary controller that is known as power system stabilizer. Okay, so let us see this. So already we have seen this equation, and from the above equation already it is for the unforced system, where we considered delta Tm is equal to 0 in this equation, right? Already we have seen this. And if the damping coefficient this is not considered, then we'll find a undamped system where the natural frequency is this. Then this is the damping coefficient d plus kd, and if it is negative due to the system condition, then there will be oscillatory instability, right? That already we discussed. And if both synchronizing and damping torque are positive for a given system, then the system will be stable and the oscillations will be damped out. So here the constant K5 becomes very important while assessing the stability. As we know, the Ks is dependent on K5 here, and also Kd is dependent on K5. And this K5 in fact depends upon your loading condition, because it is all a function of terminal voltage and the voltage where the grid is connected, right? And also other parameters are involved with it. And this K5 in fact becomes negative when the system becomes heavily loaded, and that too with a high gain exciter. High gain exciter is required, already we discussed this. So K5 becomes negative for a practical system. The synchronizing coefficient Ks becomes positive and increases as compared to K5 being positive. Hence, the negative K5, with a negative K5, the synchronizing torque improves, right? Whereas with negative K5, the damping coefficient Kd becomes negative, right? So that lead to negative damping torque. Okay, hence it gives us oscillatory instability. So this effect of negative damping torque due to K5 gets pronounced if the exciter has a very high gain, that is K is very high, right? This high gain in fact required because we need to quickly, when there is a disturbance, we need to quickly achieve the voltage, right? Terminal voltage very quickly. So therefore we need a high gain exciter. So in practical system, K5 can become negative in a heavily loaded case, and that too, the high gain exciter creates the stability issues. So the physical understanding of this is that a high gain exciter can build up the terminal voltage rapidly after disturbance. Therefore, we need a high gain exciter. So it improves the synchronizing torque, but at the same time, it creates a negative damping. So due to this, in fact, your it will not provide enough damping to the oscillation system oscillation rate. So therefore, we need another controller, supplementary controller, that is known as power system stabilizer. Okay. So this is a device. It is known as power system stabilizer that is used for overcoming this negative damping effect of the high gain exciter. Okay. So how it will eradicate, let us see. So let's consider the power system stabilizer acts as a supplementary controller to the excitation system. So that means the output of the PSS will be connected to the input of the exciter. Okay. So at the input side of the exciter, we have terminal voltage and reference voltage previously, right? As per the model we have seen, right? And now if the output will be output of the power system stabilizer will be connected to the input of the exciter. Now we have three inputs in the excitation system, right? So input to the power system stabilizer can be change in frequency or change in speed or change in power or combination of these. So the stabilizer, the supplementary controller, will have the input of change in frequency or change in speed or change in power or combination of all of these, or combination of two of these, whatever we like as per our requirement. So the output is a voltage signal and it is introduced in the excitation system to control the output of the exciter. So the basic idea of the power system stabilizer is to introduce a pure damping term. In the following equation, let us see the equation and how we can introduce a pure damping damping term, which will in fact cancel out the negative damping effect of the exciter. So we have seen this is your characteristic equation for the undamped system. S square plus omega base by 2h d plus kds plus omega base by 2h ks, right? Into delta s, delta s equal to 0. Now let us have PSS, and PSS have a transfer function GS, and the change in speed be the input to the PSS. So change in the speed be the input to the PSS. So the output of the PSS be delta V PSS. Okay. And the output of PSS is added as a supplementary signal to the exciter reference. So you can see it here. Previously, the exciter equation we write like this, right? TA d by dt of delta EFD is equal to minus delta EFD plus K into delta V reference plus delta V PSS minus delta V. Previously, this term was not there, delta V PSS. Now it is added because we are giving this PSS output as the input to the exciter. So therefore now it is becoming delta V reference plus delta V PSS minus delta VT. This is your terminal voltage which is fed back to the excitation system. So then how the PSS output VPSS affects the synchronizing and damping torque can be analyzed by finding the transfer function between delta VPSS and the electrical torque delta TE. So let us find the transfer function. So to get the transfer function, let us assume first delta equal to 0 and delta V reference equal to 0. Okay. Then the following equation can be written as this. We can see this is the equation when delta EQ dash, already we know this equation, previously we have derived, and also we know this equation, delta EQ dash S and delta EFDS. Delta EFD already we can find from this equation. From this equation we can find, right? And now from this equation, if we'll assume delta delta is 0, S delta EQ dash S will be equal to this, right? And from this equation, just after some manipulation by substituting delta delta is 0 and also delta V reference as 0, but delta V reference will change. It will be substituted. Even if it will become 0, it will be substituted by the output of the PSS, that is delta V PSS. So therefore, this equation I can write as delta EFDS. In fact, this is a combination of delta V reference plus delta V PSS, right? So now if delta V reference becomes 0, there is no change in the reference quantity. So we can write this equation as delta EFDS equal to minus K6 by 1 plus STA delta EQ dash S plus K by 1 this delta VPSS, right? So this is the equation we'll get from here, right? So now if this is in fact the substitution of delta VT, right? Okay, because from this equation we'll get the equation in terms of delta VT and delta V reference and delta VPSS, and the delta VT is substituted by this K5 delta delta S plus K6 delta EQ dash S, right? So now this is your delta EFD. If I'll substitute this delta EFD again here in this delta EQ dash equation, okay, now your delta EQ dash equation will look like this. It will be in terms of delta VPSS, right? So now we know the torque equation. This is delta T is equal to K1 delta delta plus K2 delta EQ dash. Okay, and delta EQ dash S will become equal to this. So now if we'll substitute again here delta EQ dash, your equation will become this, right? So your torque equation, and now we got the transfer function between the output voltage of the PSS and the electromagnetic torque developed in the generator, right? So now a little modification of this, if we'll do some manipulation by dividing K3 in numerator and denominator, we'll find this equation, right? That will be K2 by K by denominator. This denominator can be written as this into delta VPSS, right? So for Huygens-Exciter, this is the fact. Considering this fact that 1 by K3 is very much less than K6, then we can neglect this term, right? Not neglect, this will become 0. In fact, this will be neglected in term as compared to K6. So therefore only K6 will remain. So considering this, we'll find again delta T as equal to K2 by K6, 1 by 1 plus STDO dash by K6, 1 plus STA delta VPSS, right? So now, since the PSS has a transfer function GS, we know that the PSS looks like this, GS, and the input is delta omega, output is delta VPSS, right? So now what will be the transfer function GS, so that we'll get a damping term that will in fact neglect the damping effect produced by the exciter, negative damping effect by the exciter. So this is your equation for delta T. Now if we'll substitute delta VPSS in terms of the transfer function GS, and delta omega, it will be GS delta omega. Now what will be the GS? So if it can cancel the poles here, then we'll get a pure damping term, right? So in order for the PSS to contribute a pure damping term throughout the frequency of interest in the characteristic equation, the transfer function between delta t and delta omega should be this, right? So that will cancel out all the poles here in delta t equation, right? If we'll substitute GS equal to KPSS, it is a constant gain of the PSS into the same thing as the denominator in the delta t equation, right? So if we'll substitute this, we'll get a pure damping term, right? And if we'll substitute in the characteristic equation, that will nullify the negative damping effect of the exciter, where KPSS is the gain of the PSS. Now if we'll substitute this equation, this GS here in this equation, right? So then what we'll get, let us see. So now we'll get a pure damping. We'll get the equation of delta T as K2 by K6 KPSS delta omega. So this is a pure constant term, right? K2 by K6 KPSS S delta delta, right? Now if we'll substitute this in the equation of characteristic equation, right? So this is your characteristic equation previously. Now if we'll consider PSS and substitute and find a new characteristic equation, obviously it will add this term K2 by K6 KPSS in this damping term, right? Okay, so that will in fact, it will actually help us to nullify or to negate or to nullify the damping effect by Kd, which is due to the which becomes negative because of the high excitation gain, right? So hence PSS improves the damping of the system by providing a positive damping torque. Since introducing zeros or poles alone is not possible, it is not possible in a practical scenario or practical method. So therefore, we need to take PSS as a transfer function as follows. This is your general transfer function for PSS we take. We call it transfer function along with the washout filter. This washout filter transfer function is this. This is very important in order to block the low frequency components, right? Whenever there is a steady state change, it should not affect the PSS, or it should not, the PSS should not give the supplementary control input to the exciter during the steady change. It only acts during the transient change when the frequency is more than 0.1 Hz or 0.2 Hz, whatever the threshold will set as per this washout filter. Okay, and this transfer function will be the PSS transfer function, and this N will indicate the order of the PSS. Okay. So where KPSS is the gain, TW is the washout filter time constant, T1, T2 are the lead lag network time constants, N is the number of lead lag network blocks. So this is your, in fact, this is your PSS block where we give the input, the change in frequency or change in speed, or combination of both change in speed, change in frequency, or change in power, right? So your PSS is having three blocks. One is gain, washout filter, another is lead lag network, right? So this is your output signal delta V PSS, which will be fed to the exciter. Okay. So the power system stabilizer should not operate for steady state changes in the speed, frequency, or power. During steady state change, it should not operate. Therefore, this washout filter plays very important role. So it should only operate during transients. And in order to make the PSS operate only during transients, washout filter is used. Washout filter acts like a high pass filter allowing those signals which are above the cutoff frequency. Okay. So was the washout filter time constant is chosen so that the signal with lowest frequency of the interest can be passed through. For washout filter, time constant of TW equal to 10s signals, 10-second signals of frequency 0.1 Hz and above can be passed through the washout filter. The steady state changes can be considered as DC signals and hence will be blocked by the washout filter. Let the output of the washout filter be delta VWF. Okay, so let us see the output of the washout filter. As we have seen the block diagram, the input to the washout filter is the signal multiplied with the PSS constant, gain constant, right? So this is the input to the lead lag block, right? Let the output of the lead lag block be delta PSS, then the linearized dynamic equations of the PSS can be written as this. If we'll write the linearized dynamic equation for this PSS using this block diagram, we can write very easily, considering n equal to 1. Considering only one lead lag network, n equal to 1, we can write this linearized equation, right? So your delta VWF dot will be equal to minus 1 by TW delta VW plus KPSS delta omega dot. So from this equation, from this transfer function block diagram, we can write this equation, right? And again, from this equation, we can write this equation. This will be nothing but delta PSS dot will be equal to minus 1 by T2 delta VPSS plus 1 by T2 delta VWF plus T1 by T2 delta VWF dot, right? So here we can see that delta VWF here, this equation, in fact, there is delta omega dot, right? We know this delta omega is a state variable in our state space model. Now, how can we incorporate these equations in our state space model? That we need to see. So now substituting this here in this equation, we can write delta VPSS in terms of delta omega, right? That is a state variable also. So we need to introduce one more state variable here, two more state variables here. One is your delta VWF and delta VPSS, right? So previously we had three state variables, right? And now we are introducing two more state variables. Okay. Okay. Previously four state variables we had, and if we'll include the exciter equation, that will give us another state equation, right? So therefore we have four state variables. One is your Q axis voltage, internal EMF, EQ dash, delta and delta omega, and this is your exciter output, right? So this is the model we have derived previously, right? Now we need to incorporate the PSS model into this. We have previously four state variables, so it is a fourth order system. Now, if we'll include another variable into it, that is another two variable state variables, it will become sixth order, right? So now let us substitute this. So here, this delta omega dot equation we know. If we'll substitute this delta omega equation in this equation, we can see here in this equation we'll find this delta VWF dot in terms of other state variables, right? So just by substituting this, we'll find this equation. That is your equation for delta VWF, that is output of the washout filter equation, will become look like this, right? Now it is complete in terms of all the state variables and the input variables, delta V reference and delta TM, right? And similarly, if we'll write the equation for delta VPSS in terms of other state variables, just by substituting delta omega dot instead of delta in the equation of delta VWF equation, right? So your delta VPS equation will look like this. So now it is also in terms of all the state variables and input variables. Now we can incorporate these two equations. This is one equation, right? We can incorporate here in this another variable it will be, and here we can incorporate now delta VWF dot, and we can write the equation delta VPSS dot, right? These two variables we can incorporate. Now your state space model will become a sixth order model, right? So you can see here, this is your sixth order model having 6 state variables, and your system matrix is 6 by 6. So this is for a single machine infinite bus system, and the model we considered is a one axis flux decay model, right? Flux decay model. So for this, it is your state space model, right? Now if we have ng number of generators, then we can guess what will be the order of the state, right? So your order of the state will increase because for one generator it is 6 by 6. Now for ng number of generators it will become 6 ng by 6 ng, right? This is how the order increases as we increase the number of generators. Okay, so this is what when we consider the power system stabilizer into account, right? And this is how the state space model is changed. And now if we'll do the analysis on this, obviously it will give us a improved damping of oscillation, having all the eigenvalues in a stable condition, right? So that is what we have. And from next class onwards, we'll discuss about the multi-mission system, small signal stability of multi-mission system. Then after that, we'll conclude this small signal stability analysis. Then we'll start the transient stability analysis. And as I told, the next class onwards, we'll just discuss. I will just display the recorded video and then we'll discuss. Okay. So we'll stop here. Okay. So thank you very much.